Hello, my dear students. Today we are going to present the last period in chapter 3. We are going to discuss the ionization of water, and we are going to discuss the hydrolysis of salts and solubility product. So let us start. Calculation the concentration of hydroxyl ion for weak base. My dear students, we know that ammonia is a weak base and it dissolves in water, giving ammonium ion and hydroxide ion as the equation proceeds on the screen. So at equilibrium, we can find the equilibrium constant of the base Kb equals concentration of ammonium ion times the concentration of hydroxyl ion over the concentration of ammonia. My dear student, each mole of ammonia ionizes into 1 mole of ammonium ion cation and 1 mole of hydroxide ion anion. So concentration of ammonium ion NH4 positive equals the concentration of hydroxide ion. So as the equation proceeds on the screen, the equilibrium constant Kb equal concentration of hydroxide ion power 2 over the concentration of ammonia. Since the ammonia is weak base, so the number of moles of ionized ammonia are very small, so they can be neglected. So we can say the concentration of unionized moles of ammonia equals the original concentration of the ammonia equal C. So the equilibrium constant Kb for the ionization of ammonia equal concentration of hydroxyl ion power 2 over the concentration of the ammonia gas. So the hydroxide ion concentration equals square root Kb times C, which is molar or mole per liter. For example, calculate the concentration of hydroxyl ion in 0.1 molar of ammonium hydroxide solution at 25 degrees Celsius, given that the equilibrium constant equal 1.7 times 10 to the power negative 5. Solution of the problem. As we know, the concentration of hydroxide ion equal square root Kb times C. So by substitution, so square root of 1.7 times 10 to the power negative 5 times 0.1 equal 1.33 times 10 to the power negative 3 molar. Now, my dear students, we are going to discuss the ionization of water. The pure water is weak electrolyte, which ionizes slightly as following: water molecule plus water molecule gives hydronium ion and hydroxide ion. So, my dear student, a simplified dissociation of the water can be written as shown on the screen. H2O gives hydrogen ion and hydroxide ion. So the equilibrium constant of water equal Kc equal concentration of hydrogen ion times concentration of hydroxide ion over concentration of water. Since the degree of ionization of water is low, so it is almost found unionized molecules. So we can say the number of unionized molecules is constant. So we can say Kc times concentration of water equal constant. We call it Kw equal 10 to the power negative 14. And so we can say Kw, the equilibrium constant, Kw equal concentration of hydrogen ion times concentration of hydroxide ion equal 10 to the power negative 14. My dear student, we call the equilibrium constant Kw the ionic product of water. And it states that this is the resulting of multiplying of concentration of hydrogen ion times the concentration of hydroxyl ion, which equal 10 to the power negative 14. So we can say the concentration of hydrogen ion times concentration of hydroxide ion equal 10 to the power negative 14. My dear student, as shown in the relation above, the concentration of hydrogen ion and the concentration of hydroxide ion are inversely proportional to each other. That means the concentration of hydrogen ion, when increases, the concentration of hydroxide ion decreases, and vice versa. So we can say, give reason for this question. Water has a neutral effect on litmus. We can say, because the concentration of hydrogen ion equals the concentration of hydroxide ion equals 10 to the power negative 7. So as concentration of hydrogen ion equal the concentration of hydroxide ion and their times equal 10 to the power negative 14, so we can say the concentration of hydrogen ion and concentration of hydroxide ion equal to 10 to the power negative 7. My dear student, it is difficult to use these small values with negative power of 10 in scientific and applied terminology. So we use the hydrogen exponent. Here, the pH value that represents the hydrogen exponent, it's the negative logarithm of hydrogen ion concentration. So we can say the pH value is a way for expressing the degree of acidity or alkalinity for aqueous solution. So pH value means the letter B indicates the negative logarithm, negative log. So the pH value equal negative log of concentration of hydrogen ion. So, or we can say this is equal negative log of concentration of hydronium ion. My dear student, as shown on the screen, we have the pH scale, which ranges from 0 till 14. So in acidic solution, pH is less than 7. In basic solution, pH is more than 7, while in neutral solution, pH equal 7. My dear student, some common pH values for your knowledge only. That lemon 2.3, seawater 8.5, blood 7.4, urine 5.5 till 7, saliva 6.5 till 7.5, and gastric juice 1 till 3. My dear student, as we know, Kw equal concentration of hydrogen ion times concentration of hydroxide ion equals 10 to the power negative 14. So negative log Kw equal negative log concentration of hydrogen ion plus negative log concentration of hydroxide ion equal negative log 10 to the power negative 14. Substitute the value negative log by letter B. So BKW equal BH plus BOH equal 14. Therefore, BH plus BOH equal 14. In case of neutral solution as pure water, the concentration of hydrogen ion equal concentration of hydroxide ion equal 10 to the power negative 7. So BH equals 7 and also BOH equal 7. In case of acidic solution, the concentration of hydrogen ion is greater than 10 to the power negative 7, which is also greater than the concentration of hydroxide ion. So BH here is less than 7 and BOH is more than 7, as we get the negative log for their concentration. In case of alkaline solution, concentration of hydrogen ion is less than 10 to the power negative 7, which is less than the concentration of hydroxide ion. So BH is greater than 7 and BOH is less than 7. We are going to discuss some problems, my dear students. Complete the following table. As shown on the screen, we have the concentration of hydrogen ion equal to 10 to the power negative 2. Find the concentration of hydroxide ion, BH, BOH, and the type of solution, acidic or basic or neutral. So we can solve this by the rules that mentioned above. So we can say the concentration of hydroxide ion equal 10 to the power negative 12, and BH equal 2, and BOH equal 12, and here as BH is 2, which is less than 7, so it is acidic solution. And in the second line, as we know the OH ion concentration, so the H positive ion will be 10 to the power negative 9, and the BH equal 9, and the BOH equal 5, and as BH is greater than 7, so it is basic solution. While in the third line here, the BH equal 3, so the concentration of hydrogen ion 10 to the power negative the value of BH, so 10 to power negative 3, and the concentration of hydroxide ion 10 to power negative 11, and the BOH equal 11, and the solution is acidic as pH is less than 7. And the last one, as BOH equal 7, so both of concentration of hydrogen ion and hydroxide ion equal to 10 to power negative 7, so the solution pH equals 7, so it is neutral solution. Remember, my dear student, the hydrogen ion times the concentration of hydroxide ion equals 10 to power negative 14. So if you get the power sum, it will be 10 to power negative 14. And the pH is negative log of concentration of hydrogen ion, and the BOH is negative log concentration of hydroxide ion, and the solution will be acidic or basic or neutral, depend on the value of pH, which is less than 7 acidic, equal 7 neutral, more than 7 basic, and the sum of pH and BOH equal 14. Another example, calculate the concentration of hydrogen ion and concentration of hydroxide ion, pH and BOH in 0.1 molar of CH3COOH acid, which is acetic acid, where the equilibrium constant of the acid Ka equals 10 to power negative 5. My dear student, as we know that acetic acid is weak acid, and its ionization will be in a small amount and in equilibrium with its ions. So we can find the concentration of hydrogen ion equals square root of Ka times C. So square root of 10 to power negative 5 times 0.1 equal 10 to power negative 3 molar. Then pH equal negative log concentration of hydrogen ion, so negative log 10 to power negative 3 equals 3, and BOH equal 14 minus pH equal 14 minus 3 equal 11. And then the concentration of hydroxide ion equal 10 to power negative 14 over the concentration of hydrogen ion, so 10 to power negative 14 over 10 to power negative 3, so equal 10 to power negative 11. Another example, my dear student, calculate pH and BOH for hydrochloric acid, where its concentration is 0.003 molar. My dear student, we know that the acids differ in their strength, maybe strong acid or weak acid. Hydrochloric acid is a strong acid. What does it mean? It means its concentration equals the concentration of hydrogen ion. So we can solve this problem as following. The pH minus log concentration of hydrogen ion, which is the concentration of the acid, as it is a strong acid and completely ionized in water, so all the concentration is changed into positive hydrogen ion. So negative log 0.003 equals 3.52. And BOH equal 14 minus pH, so 14 minus 3.52 equal 10 to 0.48. Another example, my dear student. Find the following for acetic acid, where its concentration is 0.5 molar and its ionization constant Ka equal 1.8 times 10 to power negative 5. And then find the degree of ionization of the acid and concentration of hydronium ion in the acid solution and the pH of the acid and the BOH of the solution. Here, the solution of the problem. As we know, the degree of dissociation alpha as Ostwald law equals square root K8 over C, and so equal 1.8 times 10 to power negative 5 over 0.5, so equal 9.5 times 10 to power negative 4. So the high concentration of hydronium ion equal square root Ka times C, or we can say Ka equal alpha square times C. So by substitution of Ka by alpha square times C, so the concentration of hydronium ion equal square root of alpha square times C, which means square root of alpha square C square, which equal alpha times C. So we can get the concentration of hydronium ion by knowing the degree of dissociation and the concentration of acid. So 9.5 times 10 to the power negative 4, which is the degree of dissociation alpha, and the concentration of the acid is 0.5. Multiplying them gives the concentration of hydronium ion, which equal 4.8 times 10 to the power negative 5. So pH here in this problem, negative log of concentration of hydrogen ion. So negative log 4.8 times 10 to the power negative 5 equal 4.32. Then pOH of the solution equal 14 minus pH. So 14 minus 4.32 equal 9.68. Now, my dear student, another problem. Find the following for ammonium hydroxide solution, or we can say ammonia solution, where its concentration is 0.1 molar and its ionization constant Ka equal 1.6 times 10 to the power negative 5. And then find the degree of ionization of the base, the concentration of hydroxide ion in the acid solution, the pOH of the solution, and the pH of the solution. Solution of the problem: alpha equals square root Kb over C. So equal square root 1.6 times 10 to the power negative 5 over 0.1 equal 1.27 times 10 to the power negative 2. And then concentration of hydroxide ion equals square root Kb times C. So equal here Kb by substitution by alpha square times C, as we did in the concentration of hydronium ion. Here the concentration of hydroxide ion equals square root alpha square times C square. So it will be alpha times C. So the concentration of hydroxide ion equal 1.27 times 10 to the power negative 2, which is alpha, times 0.1, which is the concentration. So we get the result 1.27 times 10 to the power negative 3. Then pOH equal negative log of concentration of hydroxide ion. So negative log 1.27 times 10 to the power negative 3 equal 2.9. And then pH equal 14 minus pOH. So 14 minus 2.9 equal 11.1. Now, my dear student, we are going to discuss the hydrolysis of salt solution. What do you mean by hydrolysis? It is dissolving of solid salt in water to form an acid and alkali, which the salt is derived from them. So hydrolysis is opposite to neutralization process. As the equation proceeds on the screen, salt plus water by hydrolysis gives acid and alkali, and the reverse direction will be the neutralization reaction. My dear student, we know from the lesson from the beginning in the previous period that the strong acids are hydrochloric acid and hydrobromic acid and hydroiodic acid, which is halogen acids, and also oxygenated acids like perchloric acid, HClO4, and H2SO4 and HNO3. And the weak acids, carbonic acid, H2CO3, hydrocyanic acid, HCN, and nitrous acid, HNO2. And all the organic acids are weak acids, such as acetic acid CH3COOH. While the strong bases, my dear student, are hydroxides of group 1A and 2A, as sodium hydroxide, potassium hydroxide, cesium hydroxide. That's their chemical formula, NaOH, KOH, CSOH. And also MgOHO2, BaOHO2, which is magnesium hydroxide and barium hydroxide. While the weak bases are ammonium hydroxide and iron 2 hydroxide and iron 3 hydroxide and aluminum hydroxide. Now we are going to discuss the hydrolysis of some salts. First, we are going to talk about the hydrolysis of sodium carbonate, Na2CO3. So we have good reason in this point. Sodium carbonate solution is alkaline because Sodium carbonate is ionized in water, giving weak acid H2CO3 and strong alkali NaOH. Water is ionized as weak electrolyte. As the equation proceeds on screen, H2O gives H positive and OH negative. And sodium carbonate is ionized in water into carbonate anion and sodium cation. So by adding these two equations, we get the equation that we see on the screen. Na2CO3 plus 2H2O gives in equilibrium H2CO3 plus 2Na positive and 2OH negative. Here, my dear students, sodium hydroxide is not formed because it is a strong electrolyte and it is completely ionized, while carbonic acid is formed because it is weak electrolyte and it is incompletely ionized. So the concentration of hydrogen ion decreases and the ionization of water shifts forward. Thus the concentration of hydroxide ion increases according to Le principle. So we can say the sodium carbonate solution is alkaline and turns red litmus paper into blue, and its pH is more than 7. The second example for hydrolysis of salts, my dear student, is the hydrolysis of ammonium chloride that has chemical formula NH4Cl. Here we have the reason in this point. The ammonium chloride solution is acidic because ammonium chloride is ionized in water, giving strong acid hydrochloric acid and weak alkali ammonium hydroxide. As water is ionized as weak electrolyte, so it ionized in equilibrium with H positive and hydroxide ion negative. And ammonium chloride is ionized in water as shown on the screen into ammonium ion and chloride ion. So by getting the sum of these two equations, ammonium chloride plus water gives ammonium hydroxide and hydrogen ion and chloride ion. My dear student, don't say hydrochloric acid. You have to say hydrogen ion and chloride ion because they are strong electrolyte and so completely ionized all the ions of the hydrogen ion and the chloride ion. So we can say hydrochloric acid is not formed because it's a strong electrolyte and it is completely ionized, while ammonium hydroxide is formed because it is weak electrolyte and it is incompletely ionized. So the concentration of hydroxide ion decreases and the ionization of water shifts forward. Thus, the concentration of hydrogen ion increases according to Le principle. Therefore, the ammonium chloride solution is acidic and turns the blue litmus paper into red. So the pH of the solution is less than 7. The third example here, my dear student, is the hydrolysis of sodium chloride, NaCl chemical formula. So we have given reason in this point. Sodium chloride solution is neutral. We have to say because sodium chloride is ionized in water, giving strong acid hydrochloric acid and strong alkali, which is sodium hydroxide. So water is ionized as weak electrolyte into hydrogen ion and hydroxide ion in equilibrium, and when adding sodium chloride solution in water, we find that NaCl is ionized into sodium ion and chloride ion. And the sum of these two equations gives sodium chloride plus water gives the sodium ion and the hydroxide ion and the hydrogen ion and the chloride ion. So both of sodium hydroxide and hydrochloric acid are not formed because they are strong electrolyte and completely ionized. While here the concentration of hydrogen ion equals the concentration of hydrogen ion, so the solution of sodium chloride is neutral and has neutral effect on litmus paper and pH equal 7. Now we are going to discuss the last example here, which is the hydrolysis of ammonium acetate, CH3COONH4. So we have given reason on this point. The ammonium acetate solution is neutral. The reason for that because ammonium acetate is ionized in water, giving weak acid, which is acetic acid, and weak base, which is ammonium hydroxide. So as water is ionized into hydrogen ion and hydroxide ion in equilibrium, and ammonium acetate is ionized into acetate ion and ammonium ion, so the combination of these two equations that takes place on solution, CH3COO NH4 plus H2O gives CH3COOH and NH4OH. Remember, my dear student, here both of them are formed. So, my dear student, both of acetic acid and ammonium hydroxide are formed, so they are weak electrolyte and incompletely ionized. So the concentration of hydroxide ion equals the concentration of positive hydrogen ion. Therefore, the solution of ammonium acetate is neutral and has neutral effect on litmus paper, and so pH equals 7. Now, my dear student, we are going to discuss the solubility product. My dear student, on adding solute to a solvent at a certain temperature, the solvent dissolves the solute till reach saturated solution and become unable to dissolve more solute. So on adding excess solute, precipitates in the solution and exists in equilibrium between the solute and the solvent in the solution. So the rate of solubility and the rate of precipitation are equal, and the concentration of the solution remains the same, remains constant. So the law of mass action can be applied. So the partially soluble lead bromide, for example, is dissolved in water. It will be in equilibrium with its lead ions and bromide ions. So the equilibrium constant Kc for this equation, Kc equal concentration of lead ion times concentration of bromide ion over the concentration of lead bromide. As we know, the concentration of solid lead bromide approximately constant, so we don't write it in the equation of the equilibrium constant. So the equilibrium constant Ksp equal concentration of lead ions times the concentration of bromide ions power 2. In B, note that Kcb is known as solubility product. Here, the solubility product can be defined. It is the multiplication of the concentration of the ions of slightly soluble salt, which are found in equilibrium state with its saturated solution. My dear students, we have reached to the end of our program today. I hope you understood all the points and the problems that we discussed today. So, till we meet again, my best wishes for you.